is probably not one of my favorite experiments of the semester. What we're going to be doing is making esters through a reaction that we were just talking about, namely the Fischer Esterification. And so normally the way this is done, or traditionally the way it's done, is, as we discussed, you would take a carboxylic acid, react it with an alcohol, and then reflux it for several hours, and then you isolate the ester. So we are going to do a slightly modified procedure, and instead of heating at reflux for hours, we're going to throw it in the microwave for about 5 minutes. So before I talk to you about kind of the specifics of the reaction itself, I just wanted to show you this. It's kind of a fun slide because it kind of tells you what all the different esters are supposed to smell like. So you can see there's a whole array of different things that they can smell like, ranging from pineapple and blackberry to Jack Daniels and I don't know what that is, like a log or something. I don't know. Anyway, the only thing that we're really concerned about in this grid, though, because you're all going to be using the same carboxylic acid, namely acetic acid, is the 2-carbon row. So that's the what you would expect yours to smell like. So you can kind of see, you know, along the x-axis you have all the different alcohols that were assigned, and then on the y-axis are your carboxylic acids. And like I said, since we're all using acetic acid, we're just going to kind of use that second row in terms of what we would expect ours to smell like. But the way we're going to run this is you're going to take your acetic acid and you're going to add to it your alcohol. And the alcohols were all assigned last time. And you know, I kind of put some approximate values based on it tells you the number of moles to use. You can see you're using a fairly large excess of the carboxylic acid here. But the acid catalyst that you're going to be using for this is kind of a weird one. What we're going to be using is tosic acid. And then you're going to kind of set it up like this, right? So you're going to have your round bottom flask. In the flask, you should have 4 things. You should have the acetic acid, vinegar. You should have the alcohol. You should have the tosic acid catalyst. And then importantly, don't forget, you need a boiling chip in here, okay? So you'll have those 4 things. You'll top it with the Vigru column, and then you're going to place it in the microwave. We've got 2 microwaves that are up and running right now, and then in each of them you'll see that when you open it, there's a Pyrex dish. So you just kind of set the apparatus, the glassware, in the Pyrex dish, kind of on the diagonal, and it should fit. Okay. You probably don't. I think this slide is left over from COVID when people weren't actually able to do anything. But it is a really handy resource, just kind of an FYI. This is a website, it's called SDBS, out of Japan. And it will allow, it's just a huge database. And you can look up, I don't know how many tens of thousands of structures they have, but you can look it up by the compound name or by the molecular formula. Those are the most common applications. But it'll pop, so if you type in some random molecular formula, it'll pop up with all the different isomers that the library contains. And then you can actually go to all the different types of spectra. So typically the database would have the IR, the mass spec, the proton NMR, and the carbon NMR. So you can just find all sorts of spectra for all different types of compounds. So it's a really a valuable tool. But in any case, you're not going to probably need that for this experiment because you're going to be taking your own spectra of your own product, right? So we are going to be using a microwave, and microwaves have been used in organic synthesis for a while, probably since the mid-90s, I would say. And the reason why they are used is because they offer some potential advantages. As I mentioned earlier, You could do this the traditional way, which involves refluxing for hours, or you can use the microwave where you're going to pop it in for 5 minutes. So there are oftentimes fairly dramatic rate enhancements. You can oftentimes see improved yields, improved purity, and then improved regiostereoselectivity. So the issue with the microwaves, though, is that it's highly empirical. So you might be asking yourself, well, if all that's true, they have all these potential advantages, why don't we microwave everything? And it's because it is fairly empirical. So it does take some time up front to do the kind of the method development and optimization, because not one procedure is going to work for every reaction. So you do have to spend some time optimizing the conditions, and so some people don't really want to spend that time, and so they don't do it. But what you can see is that these are truly lab instruments. This doesn't look like the microwave in the 7-Eleven where you microwave your burrito, right? They are actually, it is actual lab equipment. You know, they have all sorts of different variables you can change, and they are not exactly inexpensive. Now that said, the ones you're going to be using in lab today are like the ones at 7-Eleven that you microwave your burrito in. In fact, I think the stockroom guy a couple of years ago, when they got them, went down to Walmart and scored a Black Friday deal. But so yeah, they are just regular old microwaves, but they work. So you know, whatever. So as I said, there's a few advantages to using the microwaves. The microwave is a direct heating method. So whereas kind of the traditional heating methods are indirect, they heat by convection, so you have to transfer heat, you know, from the heating mantle through the glass, through the solvent, etc. So it's an indirect heating method, and a fairly long heating method. You know, it takes a while from the time you heat your mantle to the time you're actually refluxing, right? Microwaves are much faster and a direct method of heating. And the reason why, the source of that heating is that microwaves, being on the electromagnetic spectrum, they induce changes at the molecular level, kind of like, you can almost think of it as like a spectroscopic thing, you know? The changes that microwaves induce are changes in rotational modes. So if you have polar molecules and you put them in the presence of microwaves, it'll cause the molecules to start rotating. And this rotation causes, you can almost think of it as like molecular friction. It causes, that's what is the source of the heat. What you're going to do is you're going to get your apparatus set up. And like I said, we've got 2 microwaves working. Let's see if I can find a third one, but we'll have at least 2. So you're going to have to kind of put your name on the board, because obviously with 2 microwaves, you might have to wait a few minutes. But it is only 5 minutes per run. So with 2 and with 12 people, it shouldn't take that long. But in any case, you'll put it in the microwave. Whenever you're ready, just come and get me, and I'll dial in the right settings. You don't want to just turn it on high for 5 minutes, because that's too hot, and you'll end up with a bunch of black sludge that way. So just whenever you're ready, just come get me, and I'll put in the right settings for the 5 minutes, and after that, it'll be done. What you want to also make sure of is, after the 5 minutes, you go to claim your reaction, resist the urge to just put your hand in and grab your glassware, because it is going to be smoking hot. So what I would recommend you do is grab one of those little orange crab claw things, and also whenever you go to grab the glassware, don't just grab it by the Vigru column, okay? Because remember, there's nothing holding these 2 things together. And if you just grab the Vigru column and carry it back to your bench, there's a very good chance that the round bottle is just going to fall off, okay? So when you go to grab your glassware, make sure you're grabbing at the neck. You know, grab the round bottom flask, not the Vigru column, right? What I would recommend you do maybe is, once you get it back to your bench top, go ahead, kind of set it on the bench, hold the Vigaroo column and put a Keck clamp on them. Okay, once they're clamped together, you can hold it by the Vigaroo column, then you could just hold it under some running water to cool it down quickly, and you don't have to wait for it to cool at room temperature. Okay, but once it's cooled, you've held it under some running water, you got it down to room temperature, you're gonna pour the contents in a separatory funnel, right? Because if you think about it, what you've got in the flask at that point is your ester, which you want, and a whole bunch of acetic acid because you used a large excess of acetic acid. So you've got to get rid of that excess acetic acid that you don't want. And the way we're going to do that is by washing with large amounts of sodium bicarbonate. Now, if you think back, what you're doing here is essentially that old elementary school science project thing with the volcano. Remember, have you ever seen that? Maybe it's so old they don't even do it anymore. But they used to you'd construct a volcano and then you had some baking soda and then they would pour in colored vinegar and it would erupt, and because baking soda and vinegar creates a whole bunch of carbon dioxide. Well, that's exactly what you're going to be doing as you pour in the baking soda solution, this bicarbonate solution, into your SEP funnel. So, two things about that. Number one, do it slowly, because you don't want your separatory funnel erupting like the elementary school volcano. And number two, when you go to shake the SEP funnel, you have to make sure you are venting with every turn, okay? Even after the bubbling slows, as you agitate the funnel, you're gonna start generating more CO2. And that's gonna cause a lot of pressure to build up in the SEP funnel, a lot more than normal. And so as you're turning, with each turn, you wanna make sure you're opening the SEP funnel to allow that pressure to be released, all right? So you're gonna wash twice with sodium bicarbonate, and then you'll wash a third time with water. All right. At the end of that, you'll drain off the organic layer, which should be just your ester. You'll take and you'll dry it over sodium sulfate, and then you can decant it into something that is pre-weighed. All right. And then that would be a good place to stop. You can store it and then come back on Wednesday and you'll do the characterization of the ester. Okay? Anybody have questions on that?
We're supposed to wash it 3 times with sodium bicarbonate or 2?
Whatever it says in the lab manual, does it say?
It says 3 times.
Does it say 3 times? Okay, then do it 3 times. Yeah.
Do you still want us to do it with water?
Yes. Yeah, do it with the water.
Okay, so 4
Mhm.
times.
Are we doing boiling point when we're
No,
characterizing?
don't worry about the boiling point. In terms of characterization, you're only going to do get the yield as always, IR and NR. All right. Okay. If nobody has any questions, then we can go ahead next door and get started.